Good morning. Okay, we'll get started in just a second here. I'm just updating the website. Good morning. Okay, we'll get started in just a couple more minutes. Just gonna wait for a few more people to stream in, and then we'll jump to it. Yeah. Okie dokie. All right. Okay, look at that. Wow, 21 people. Perfect. Okay, let's jump to it then. So last time we started looking at prime power decomposition, right? So we would take a number and write it as its prime power decomposition, right? So in other words, we decomposed it into prime powers using factor trees. So that's what we did yesterday, and we just started to look a little bit at LCMs, and well, we're going to look at GCFs today as well. So what I'm going to do today is I'm going to show you this method of finding LCMs and GCFs using a table. The table is fairly straightforward to generate, and once you have this table, then calculating the LCM and the GCF is quite straightforward, and it's just a really easy way to organize all of your data. And it's possible that you're already like really good at calculating LCMs and GCFs, and you know, the table is one of those things that really helps your understanding, and after you do it quite a few times, maybe you don't need to use the table anymore. But I think that the table is still going to help. So I'm gonna show you how to do that. So let's see if I can just grab a few examples for us to burn through. So let's see here. What if I did? Yeah, let's calculate. So let's calculate just as a kind of a warm-up example. Let's calculate the LCM and GCF of, let's see here, the LCM and the GCF of, how about 27 and 45. 27 and 45. Okay, so this is what we'll do. So we'll start off. So step one is to find the prime power decomposition of both integers. Okay, so I'm gonna. This is how I like to organize it. I write the first number over here, and I give myself a little bit of space, and I write the second number over there, because we're gonna have these two factor trees, right? So all of this area right over here is gonna be like this one, and this area over here is gonna be that one. So these might overlap a little bit. I might actually have to move this one over here a little bit, but that's probably just enough room there. So 27. So we're just looking for factors of 27. So 27, that would be 3 times 9, and 3 is prime, and 9 is 3 times 3. Both of those are prime. Okay, going back to 45. 45 is 5 times 9, 5 is prime, and 9 is 3 times 3. Okay, so 27. Oh, look who decided to show up. Look, you guys missed it. Yesterday was Goose's birthday, so she turned 3 yesterday. So maybe wish her a little happy birthday. She had a great birthday party. We had we gave her some wet food, and we played with her sister. It was a super fun time. We had a blast. Okay, oops, and looks like Goose is now erasing my work. That's okay. Okay, so 27. 27 is equal to 3 to the power of 3. Okay, that's good. Goose, it's unbelievable how cute she's being right now. She's just lying right beside me. Oh my goodness. It's surprising that I get any work done at all with this cute little bundle of love right beside me all day. Goose, how am I supposed to do any work? Okay, excuse me. So 27 is 3 to the power of 3. 45 is equal to, well, I've got 2 3's, right? It's 3 to the power of 2, right? 1, 2, 3 squared times 5. And I'm going to write 5 to the power of 1. Okay? Now, this is the table that I'm talking about. So the table, so this is going to be step 2, I guess. So step 2 is to make a table. So make a table. Okay, so the table is going to look something like this. So I'm going to write the first number, which is 27 over here. I'm going to write 45 over here. And now the way the table works is that I'm going to be writing all of the prime powers that are a factor of each. However, each column here has to... Goose, go... I don't want you to go away because you're too nice, but you also have to let me work. So each column is going to correspond with a particular prime number. So the way I like to do it is I like to go from the smallest prime number up to the largest prime number that is in our prime power decomposition. So the first one would be 3. So this column, and you don't have to write this in your tables when you're actually doing it, but I just want to tell you that this column right here is going to be all about the 3's. And so the first one, I've got 3 to the power of 3, because that's what 27 has. And 45 has 3 to the power of 2. Okay? Now, the next column over here, well, the only other prime number that we have to deal with is 5. So I've got 5 over here. And, oops. Okay, so we've got 5 over here. And what I'm going to do is I'm going to write, okay, well, I've got 5 to the power of 1. And the other one, I don't have any 5s. So there's a few things that you could do. If you want, you could leave it blank. That's perfectly fine. I prefer to do this. I like to think, okay, I have 0 5s. I have 0 5s. So I've got 5 to the power of 0. By the way, I don't think that we've looked very much at exponent laws. But if I take any number to the 0th power, that is equal to 1. A huge misconception is to believe that that is equal to 0. 5 to the power of 0 is not equal to 0, it's equal to 1. In fact, any number to the power of 0 is equal to 1, except 0 to the power of 0. That's what we call an indeterminate form. And it looks weird because Goose is just lying right on top of that part of the iPad. So 0 to the power of 0 is an indeterminate form, so we don't really talk about that. You don't really talk about 0 to the power of 0 until you're in calculus. Well, in calculus, that's a big topic. How do you deal with 0 to the power of 0? We don't have to worry about that for now. In the meantime, all we have to worry about is that any non-zero number taken to the 0th power or to the power of 0, that's equal to 1. All right? Oh, okay. Oh, look at that. I kind of ignored the chat for a minute. Oh, thank you for all the beautiful birthday wishes to Goose. That really means a lot to her. You guys are very, very sweet. Wait, are they like GCF or LCM factor tables? So they're similar to that. Yeah, it's kind of like a factor table. Yeah, and yeah, 0 to the power of 0. 0 to the power of 0 is indeterminate. We don't talk about that until later. Just know that 0 to the power of 0 is it can mean different things. It can mean different things. In fact, it can mean anything you want it to. So, I mean, that's kind of an abstract idea, but it is something that you do deal with in calculus. But we're not in calculus right now, so we're going to ignore 0 to the power of 0. We are going to look at 5 to the power of 0, or any prime number to the power of 0. That's just equal to 1. Okay, so now we've made our table. Now step 3, I'll just write step 3 over here. Step 3 is to, well, if we want to look for the LCM, what we want to do is we want to circle largest power. Okay, sorry Goose, I gotta scoot you over. So what we're gonna do is we're gonna circle the largest power in each column. Okay, and for the GCF, we are going to circle the smallest. Oh my gosh, we're going to circle the smallest power in each column. Okay. So let's go ahead with that. I'm gonna make the LCM in red and the GCF in green. So the red one, I'm gonna say, okay, well, if I'm going to have any kind of multiple of 27, it's gonna have to have 3 to the power of 3 as a factor, and that's already kind of eclipsed or already included with the 3 squared, so I don't have to circle the 3 squared. And the 5 to the power of 1, that's the largest in that one. So the LCM is equal to 3 to the power of 3 times 5 to the power of 1. And the GCF, I'll do that in green, it's all the other ones right over here. So that would be the smaller one over here and the smaller one over here. So this would be 3 squared times, well, we could do 5 to the power of 0, but 5 to the power of 0 is just 1. I'm just including it just so we can see that 0 is smaller than 1. So we're just going to forget about it and just leave it as is. So the LCM is, oh my gosh, what are they doing over there? Sorry about this. Just a few distractions. Okay, so the LCM is going to be, well, 27 times 5. Let's see what that's equal to. Should be able to do that in my head, but I am not going to do that right now. Okay, clear. 27 times 5 equals 135. 135, and the GCF, well, 3 squared is 9. Okay, and that's that. That's how we do that. Now, yeah, we could talk about LCMs and GCFs all day, but this is kind of like a preliminary topic to what I want to sort of begin talking about next. And are they fighting the box? I think Kima got in the box by herself, and then Goose is kind of waiting her turn. Here, wonder if you can see that any better. Yeah, so Goose, you can kind of see Goose is there she is, just kind of waiting patiently for her turn inside the box, and Kima is she's inside the box. But, oh, there she is. She just poked her head out. Kima, say hi to everyone. What you doing in there? Hi, sweetie. Hi, say hi. Hi, Kima. Okay. Yeah. So that's my life, playing with cats all day. Oh, and of course, I'm noticing now that you couldn't see my writing. That's what I wrote earlier. Oops. What the heck? Oh, oh my goodness. I changed classes. There we go. Oh yeah. So the GCF, we're gonna circle the smallest power in each column, and that's that. That's how you find the LCM in the GCF. So and you don't have to use these tables. I think that the tables are just nice to organize your thoughts, and it kind of gives a procedure that you can follow, that you don't really have to worry too much about what's going on. You can kind of just follow the procedure, and boom, you get the LCMs and GCFs. Yeah, okay. Yeah, we got lots of stuff going on in the background, eh? Lot of fun antics. Yes. Okay, let's... Okay, just trying to think about if I should keep going with some of these factor stuff, or if I should really just jump into the next topic, because this is a review, and I don't like in all of the homework that I've seen, you guys do. Oh, hi. Do you hear that? They're awesome. They love to fight and everything. Okay. Yeah. In any case, all of the stuff that I've seen you guys do, I don't have any concerns about you guys finding factors and reducing fractions and that kind of thing. But it is good that I know that you can do this. It seems like in the chat and also in the exit slip, it seems like people are okay with this. So we're gonna jump into our next topic, which is square roots. Okay, we're gonna talk a little bit about square roots. I say we rush through all the topics and try to finish everything by May. Oh yeah, wouldn't that be great? Maybe I can just go until like midnight tonight. We'll just power all the way through, just finish all of grade 9 advanced. We'll have like one huge final exam starting at midnight. It'll be due at 6 a.m. and then we'll be done. What do you say? Maybe we do that, eh? And then I mean, that would be fun, but then what would you do? What would you do for May and June, right? That's two months of like we're all stuck inside. Although I did hear that they're opening up patios and you can get a haircut now, and there's a few other amenities that you can take part in. Oh, no exam. Oh, this guy wants to eat his cake and have it too, right? You know that expression? It means you want to have it both ways, right? Because you can eat a cake, but once you eat your cake, you can't have it anymore. Your cake is gone, and you don't get to look at your beautiful cake. Play video games and chill with people at parks. Oh yeah, that sounds like fun. June's gonna be crazy. Yeah. Oh, golf. And I'm looking a little bit further up, higher in the chat. Looks like I'm starting to make someone start to like cats. So, as far as I'm concerned, as any kind of metric of how good a class is, if a class is able to make you like cats, then I think my work here is done. I think we can call this a success story. That's what Goose says, anyways, and Kima too, right, Kima? Come here. Come here. Come say hi to everyone. Yeah, Kima doesn't get anywhere near the same amount of airtime as Goose. Goose gets all the attention. Kima gets she's really shy, and she's also a little judgmental, and but she's also just very, very loving. This was our first cat. This is the first cat that I ever had, and she's very special, very, very kind and beautiful. Okay, bye, Caddy. Okay, let's see here. Can hang with friends, yeah. Conclusion of class. I watched Kobe swing. I'll be doing that by June. Okay. Oh, are you in Mr. Mr. Summers' art class? Oh, this is so great. I'm so glad to hear these things. It really helps me kind of be motivated when I hear that people are enjoying this, and you know, that's a large part of why my cats are kind of at the forefront of this. Oh, you're in Mr. Dewick's class. Oh yeah, of course you are, because you're in grade 9. Yeah, for some reason I thought that Mr. Summers did grade 9. Yeah, Mr. Dewick is awesome. Mr. Dewick is super cool. He sends me music all the time, and he's got an excellent taste in music. I just love his taste in music. Anyway, let's. I don't know if you can hear that, but Kima's being adorable. Okay, so you're in Mr. Summers' class. Okay, cool. Okay, yeah, I thought that he did. I thought that he did grade 9. So I guess they must split the grade 9s. Anyway, let's start talking about square roots. Okay, so this is kind of going to be a new topic, and we're not gonna go like all out with this topic. It's just gonna be Kima, why are you being so cute? I don't know if you can see her, but she's kind of just like rolling around on the carpet and being adorable. Okay, so we're gonna sort of just touch the tip of the iceberg here. We're not gonna go off in the deep end with square roots, because this really is like a topic that you'll investigate quite a bit next year. Next year, this is like a major topic, but I want to get you a little warmed up so that next year you'll be a little bit more prepared for it, and you'll have known a few things. So this is what we're gonna talk about is square roots. Square roots. Okay. Why are you being so sweet? She's just frolicking on the carpet. Or the rug, rather. Just making little chirpy sounds. That's what she does when she's happy. That's how you know she's happy. So square roots. Square roots. Okay, let's talk about square roots. So what are the square roots? So a square root, I mean, I think we all have some kind of idea of what a square root is, right? A square root is the opposite of a exponent of 2. Or in other words, i.e. a square. Okay? So for example, I think that one of the most popular square roots is 81. I don't know why, but I remember when I was in grade school, and that was kind of like the ultimate test of intelligence. Like when I was in grade 1, it was like, oh, what's the square root of 81? And then people were like, 9. So 9 squared is 81. Therefore, the square root of 81 is equal to 9. Simple as that. Okay. I want to make something very clear here, though. So I'm just going to write a little beware. Okay, and I'm not sure if you've already seen this. I've taught this topic to grade people as young as grade 8, and I've taught this to people as old as university students, and it seems like pretty much everyone has this misconception, and it's an honest misconception, and if you already thought this, that's okay. You're allowed to make mistakes, but I want to set it straight. Okay, this is a really important idea that lots and lots of people get kind of thrown off on. So it is true that if I took positive 9, and I know that we don't usually write the positive symbol in front of a number. But just, I want to be explicitly clear that we're going to be talking about the dichotomy between positive and negative numbers here. So it's true that positive 9 squared is equal to 81, and negative 9 squared is also equal to 81, right? Both of those facts are true, right? That's undisputed. Because negative 9, like negative 9 squared, that's negative 9 times negative 9, and a negative times a negative, as we know, is a positive, so this is equal to positive 81. So yes, it is true that there are two possible values whose square is 81. That's absolutely true. That's a fact. It's right there. However, it is not true. It is not true. It is not true that the square root of 81 is equal to plus and minus 9. That is not true. Okay? So people often think that the square root is saying, okay, the square root of a number is all of the values whose square is 81. That's not true. This is not true. So I want to be very clear that this is not true. So, and I always hesitate writing things that aren't true in my notes, because I'm afraid that someone is going to write it down and kind of skip the not true part and just write, oh yeah, the square root of 81 is plus or minus 9. By the way, plus or minus 9, that means two numbers. That's a shorthand way of saying plus 9 or negative 9, right? That's what that means, that there would be two values that make that true. This is not true. So this square root symbol, the square root symbol means principal root. Oh yeah, and I think it's principal, like Mr. Hutchison. The principal square root. Okay, so the principal square root means, so this means, basically, I mean, the long story short, just means the positive version. Okay, it means the positive version. Okay, so there's this, I mean, and the reason why this is a misconception, is because, okay, so I'll write source of misconception. And by the way, it's not just about the number 81. It's the fact that a lot of people think that when you take the square root of any number, you'll get the positive and negative version of it. Okay, so this is the source of the misconception. So the source is, well, let's say that I wanted to solve x squared is equal to 81, right? Like, let's say I gave you this algebraic equation to solve, and you would say, oh yeah, I know how to solve that. You know, I'm looking for all the numbers whose square is 81. Well, x would be plus or minus 9, right? And that is true. This is absolutely true. This is true. Okay? It's absolutely true. But I think that what people mistake is that they add in this extra step. They say, okay, well, if this x squared is 81, that means that x is equal to the square root of 81, and then the square root of 81 is plus or minus 9. No, that is, so this part is not true. This is not true. This is where people make the mistake. Okay? So the intermediate step that is true is, well, I'm just going to write the whole thing out again. If we have x squared is equal to, x squared is equal to 81, well, then x is equal to plus or minus the square root of 81. Okay? And the square root of 81, like this part in red here, the square root of 81, this is just a positive value, but this plus or minus sign here that I'm writing in blue, the plus or minus sign is signifying that there's two of them. Okay? So this is the source, this is a major source of confusion, is that people often think that the square root symbol gives you two values. It doesn't. It gives you one value. It gives you just one value. Okay. Okay. So that's a brief little introduction to square roots. I want to talk about how factoring, like how does factoring play into square roots? Oh, look who came to say hello. Hi, Goosey. Okay, how does factoring play into square roots? How does it play into square roots? Well, I'm going to give you a fact. Okay, so this is a fact that we just have to sort of accept. We're not going to like derive it or anything like that. So the fact of the matter is that if I have for any numbers A and B, okay, we have two facts. The square root of A times B is equal to the square root of A times the square root of B. Okay, it's a fact. Okay, so that's a really nice thing about square roots, is that if you have a product inside your square root, you can split that product up into two separate square roots. Okay, we also have this fact, the square, Goose, oh my goodness. She likes to sort of try to grab my pen while I'm writing. The square root of A over B is equal to, Goosey, oh my goodness, is equal to the square root of A over the square root of B. So that works really nice. Okay, now I'll give you another caution. So the caution is this: the square root of A plus B is not equal to the square root of A plus the square root of B in general. Okay, so there might, like what I mean by this part. Oh, Goose. Oh my goodness. In general. Okay. What I mean by this in general portion, what I like the purpose of me saying in general is that you may be able to find a specific set of numbers where that actually does work. For example, like if A was 0 and B was 1, then yes, the square root of 0 plus 1 is equal to the square root of 0 plus the square root of 1. Like in that very particular case, sure, yeah, that works. But in general, this doesn't work. So you cannot split up a sum inside of a square root symbol into two separate square roots, okay, as a sum, okay? Just doesn't work. So just because you can split out a product does not mean you can split up a sum, okay? And that's Goose moving it. She's got her paw on the iPad, and she likes to kind of stretch out her paws a little bit, and she just moved the screen. Okay, Goose. Here, let me just give you a quick little screenshot of what my desk looks like right now. It's a little bit ridiculous. Yeah, there she is. So like this is, I just took my case off. This is where my iPad is, and she just likes to have her paws like right on top of my iPad, and just, you know, just in case she wants to do something. And then when I'm writing, like this is what she does when I'm trying to write. And then I have to do this, and then she thinks I'm playing. She thinks I'm playing a game with her, but really I'm trying to draw. But it's a very fun game, and she's really good at it. She's very experienced. She has lots of practice playing the pencil game. Right, Goose? Yeah. Okay. Oops. Okay, how do I get back here? Okay, there we go. All right. So let's talk about how we can use factoring. So you can kind of see what's going on here with the factoring is that, like, if we were able to factor a number like this, like here I've got two numbers that are a factor of A times B. So if I can split those up, then I can split it up into easier square roots. So we can simplify square roots by factoring out perfect squares. Okay, so let's do an example and let's see what we could do here. Well, first of all, you know what? Let's actually, before we do that, let's just review. Let's review some perfect squares. Now, in math class, people tend to think that in math class you have to memorize a whole bunch of stuff. That's just false. It's not true. In math class, math has got to be one of the topics that you have to memorize the least amount of stuff. Like, I don't want you to think that I don't like chemistry, I don't like biology or something. Those are incredible topics, and especially in like during a pandemic, those are like obviously the areas of science that are going to save us. But if you look at a chemistry class or a biology class, the amount of stuff that you have to memorize is gargantuan. You have to memorize a whole bunch of stuff. In math, what do you have to memorize? Like your times tables, like that you memorize like in grade 4. And like what's the last thing that you had to memorize, right? Like there's not a lot of memorizing. It's more understanding. That said, I still want you to memorize a few things. So what I'm going to get you to do is I'm going to get you to memorize these numbers, okay? So I'm going to tell you to memorize. I need you to memorize these perfect squares. These perfect squares. Okay, so 0 is a perfect square because 0 squared is 0. 1 is a perfect square because 1 times 1 is 1. 4 is a perfect square because 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. What am I at? 7. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. 11 times 11 is 121. 12 times 12 is 144. 13 times 13 is 169. And I think that at that point you're probably good. If you wanted to, you could do the next one, which is 196. Oops. 196, that's 14 squared. But I think at that point, like you could keep going, obviously, like 225 is the next one, 15 times 15. I think that if you memorize this list, you'd be golden, right? But at the bare minimum, what I require you to memorize is up to 144. Okay, so this is the minimum. This is what I require you to memorize, and these are all values that are in our times tables, right? Like this is still I mean, maybe you only did up to 10 times 10 in your times tables, in which case I'm asking you to memorize two more numbers, 121 and 144. Okay, so I need you to memorize these perfect squares, and when I say memorize them, I don't mean like learn how to generate them, right? I don't mean like, okay, so if I gave you 5 minutes, would you be able to recreate this list? Yes, I know that you could easily recreate this list. I need you to know that these are perfect squares, and I need you to be able to do something like this. So if I had like a number like 75, okay, I need you to be so familiar with this list that you'd be able to say, oh, I know 75, that's 25 times 3, and 25, that's a perfect square. Okay, that's how familiar with these I need you to be. That when we're looking for perfect squares, not only do we know what the perfect squares are, but they're so ingrained in our memory that we can be like, oh, I can see a factor of this other number that's a perfect square. I can pull out a perfect square from here. Okay, that's how familiar with these numbers I need us to be. Okay, so yeah, I would say go up to 144. And if you can, memorize those extra 3 numbers, and it'll really help. It'll really help you out. Okay. Okay, let's see here. Yada yada yada. Okay, I'm gonna do one example, and then we're gonna call it quits because we're just about out of time. So let's do this example. E.g., calculate. Calculate the square root of 441. Okay, let's calculate the square root of 441. And look at that, that's actually 144 backwards. So maybe the square root of it is 12 backwards. Maybe the square root is 21. Wouldn't that be funny, right? Because remember, the square root of 144 is 12. Is it true that the square root of 441 is equal to 21? Maybe. I don't know. Probably not. Probably not. But let's try. Okay? So what we're going to do is we're going to start off by making a factor tree. So I've got 441. Any factors of 441 that you see? Well, this is where some of our divisibility laws are kind of going to come into play. So I can see, so one of the first divisibility rules that I test is 2. Like, is this number divisible by 2? No, it's not. It's an odd number. It ends in 1. So let's see here. Is 3 a factor? Is 3 a factor? Yes, it is, because 4 plus 4 plus 1 is 9, and 9 is divisible by 3. In fact, because of that, 441 is divisible by 9. So let's factor out a 9, and then let's see what is left over. So 441 divided by 9 is, well, 9 goes into 44, what is that? 4 times with 36, and that would be 8. And then, so yeah, it would give us 49 left over. Okay, and then 9 is 3 times 3. This is factorable, and this is 49 is 7 times 7. So 441, the square root of 441 is equal to the square root of 3 squared times 7 squared. Okay, so that's nice because the square root of 3 squared times 7 squared is equal to the square root of 3 squared times the square root of 7 squared, which is equal to 3 times 7. Or 21. Look at that. Beautiful. Okay, so that's kind of the style of questions that we're going to be getting into. We'll do a few more examples like this on Tuesday. Now, a couple things that I should let you know before we go. There will be a new assignment on Google Classroom today. So I haven't finished making it yet, but it should be up by the end of the day. I'm thinking it'll be due. I'll give us one more class, so if you want to ask any questions, we can kind of address that in class, and it'll be due in the following class. So we have a class on Monday, so it won't be due on Monday, it'll be due on the following class, so it'll be due on Wednesday, okay? So stay tuned on Google Classroom. Make sure that you look at that, and what I'm going to do right now is I'm going to ask you, let's see here, to tell me, so the exit slip for today, exit slip, and I've noticed on YouTube, it's weird. The thumbnail on a lot of my videos is the exit slip. I don't know why. I wonder if maybe it's because people pause so that they can, write the exit slip down, and then maybe YouTube says, oh, this is an important frame because everyone is pausing on it. Is it an assignment for marks? Yes, it is an assignment worth marks. It'll be on Google Classroom. Not a test, it's going to be an assignment. Okay, so stay tuned. Anything on Google Classroom is going to be worth marks. Okay, so I do assign a lot of sort of, homework that is just for you to do on your own time. I'm not going to mark that, but an assignment, which is on Google Classroom, yes, I will be marking that, and it will be worth marks. Okay, so I want you, for the exit slip, is to calculate Square root of 324. Okay? 324. Let me write that nicely. The square root of 324. Okay? So that's your exit slip for today. And that's supposed to say calculate, not calculat. Yeah, that's your exit slip today. So stay tuned for the assignment. It's not going to be like a crazy long assignment, but it will cover a lot of the topics that we've been talking about over the past couple of weeks. I just want the answer. Yeah, don't bother like showing me all your work. I just want the answer. So I mean, if you're really lazy, you could punch it into a calculator and just tell me. If it's a decimal, give me, I don't know, 12 decimal places. Yeah. So yes, you could punch that into a calculator. Absolutely. I'm well aware that this is a very straightforward exit slip. But I think it would be a good idea to try using a factor tree and see if you can calculate this using a factor tree. It's just not worth it to me to get you to show your work on an exit slip, because I'll be honest, I'm not going to look at your work on the exit slip. The exit slip is really more of an attendance thing. I really just want to know how many people are watching the videos. So I'm going to sign out now, and I'll talk to you guys on Monday. So have a good weekend, and please stay tuned for what am I trying to say? For the assignment, which will be on Google Classroom by the end of the day. And if you have any questions, don't hesitate to reach out. And okay, bye-bye.